times v1 plus w1 plus 2u2 v2 plus w2, right? Okay. So now let's try to do some stuff with this. So what I'm going to do, since again these are real numbers, right? So I can distribute
Hey, I'm
this thing
recording a
right
class,
here
so I'll be
and
back in a
there,
second.
Sounds good.
and then also I guess this thing right here and there, right? So if I do that, u1 v1 plus u1 w1 plus 2u2 v2 plus 2 u2 w2, right? Okay, so now we have this. So remember, our goal is to make it look like this thing right here, right? So if you're having trouble like trying to make it look like a certain thing when you're trying to show these things, just write out what this looks like right here, right? So that thing is gonna look like u1 v1 plus 2u2 v2, right? And then this thing right here is gonna look like, well, u1 w1 plus 2u2 w2, right? So just imagine what they look like at the end, and then try to make that and try to like go into these intermediate steps and try to rearrange everything to make it look like this. So I mean, you can see from here that I'm gonna gather this one and this one together, right? Since these are real numbers, I can just commute addition, and then I'm going to commute, and then I'm going to gather this one and this one together. So if you do that, you get u1 v1 plus 2u2 v2, and this is going to be plus u1 w1 plus 2u2 w2. Well, what is this? What is now? What is this thing right here? Well, that's just going to be the inner product of u plus v. I mean, v, right? And then this is going to be plus, well, what's this now? Well, this is going to be the inner product of u and w, right? So you show that this thing indeed satisfies that property. Okay. What about the next one? Well, now we have to show that this is true for I guess, C, a scalar, right? So we just need to show that it like goes in, I guess, in the first component. So I guess, so number 3. Let's take this one. So we want to show C U V is equal to, yeah, for sure. Here, let me just finish writing this. So we want to show this, right? Again, it always goes back to just expanding out what you've got. Right? So, so if I give you an inner product to show it's so if I say show it's an inner product, you do this, okay? Now, there might be sometimes where I might ask, is this an inner product, right? So I guess from there, for the strategy we want to do is check the easy ones first and see if they break. If they break, then obviously it's not. If it doesn't break, yeah. So is this the page you wanted? Or okay, perfect. But yeah, so let's move on to the so here then we get, oh yeah, and this C is a real number in this case, right? So we have C U V. What is this equal to? What's going to be C equal to C times U1 V1 plus 2 U2 V2. Okay. So now what we can do is you can distribute. So you get C U1 V1 plus 2C U2 V2. Okay. So now what we can do is, well, associate. These numbers are associative, right? So I'm going to associate this part and this part. Remember, real numbers are associative and with multiplication, so it doesn't matter which one you do first, right? So if I do this, then I mean, you can then clearly see that this is going to be inner product of CU1 with sorry, C with CU V. Does everybody see that? Right. So I just put them in the U1 U2 components, and then that comes out as a as the inner product. That's how C gets stuck in that inner product. And then I guess the last thing I guess I'll maybe show. So maybe just two more things, right? So, or actually, just this last thing, right? So we just need to show that any vector with any vector inner product with itself is always positive, and if it's 0, then the vector has to be 0. Okay, so now do 4. Okay, so we need to show that U, I guess, with itself is always positive, and I guess U equals 0 if and only if U is 0, right? Okay, so let's first do the first thing. So do the inner product with U with itself. Well, this is going to be U1 times U1 plus 2 U2 U2. And this is going to be U1 squared plus 2 U2 squared. Okay, so is this thing always positive? How I have it written here? If it is, why is it true? Yeah, exactly, right? It doesn't matter if, yeah, exactly. So it doesn't matter if the components are negative or positive. Any number squared is just going to be, well, real number. Any real number squared is always going to be positive, right? So a positive number plus a positive number is always going to be positive. So this is definitely always greater than 0. So now, moreover, if U is equal to 0, then U1 squared plus 2U2 squared is equal to 0, right? So what is the only way that this thing is going to be 0? So remember, now so typically, so this isn't linear, right? So you can't just solve it in how we usually do it, right? Why? So is this always 0? I mean, sorry, does this mean that the vector has to be 0? Would it be 4U squared since it would be 2U? No, because if you look up here, this is taking the spot of U now, right? So it's just going to be, so you just replace wherever the V1 and V2 is with U1 and V2. So it should just be, yeah. But anyway, so it's u1 squared plus 2u squared equals 0, mean u has to be 0. Yes, yes, it is. And why is that? I mean, is there any, so I mean, if you had maybe like x plus y equals 0, the only way that this is going to be 0 is if x equals negative y, right? So you can't, so if x was 1, then y can be negative 1 and still give me 0. But notice that only happens if I'm allowed to choose negative numbers, right? Is u1 squared and u2 squared ever going to be negative? No. So really the only way for me to do this is if they're all 0, right? So this implies that you can say u1 is 0 and u2 is 0. So u has to be 0. Okay, so this is, I mean, so that's, okay, so this example is served as for two purposes, right? So it serves as a way to show you, okay, this is how you show something's an inner product, right? So you check these 4 things like a checklist. Once you check them, the thing is an inner product. So this thing can give you distance, angles, and all that other stuff, right? But the second purpose was this. So I did it in the vector space R2. What was the remember what was the inner product in Rn again? Just like the standard one that you knew for like I guess a while. Dot product, right? So this clearly isn't a dot product, right? The dot product that we defined, this guy right here, that one isn't a dot product, but it's a different inner product on the same vector space. So again, so what this means is that inner products aren't unique, meaning that there isn't just one for every vector space. They can define multiple ones, and they all are equally as valid as the other ones. Okay, so inner products are not unique. I guess you can say that. Okay. Obviously, not everything that you define will be an inner product, right? So you always have to check it. So if you give me one that you tell me here's the rule for this so-called inner product, and I checked all the axioms, and it shows that not all of them are satisfied, then it's not an inner product. So let's do an example to see that actually. So 5.2.2. So maybe define again listing, let's say on R2 as, I don't know. Oh, I guess I should maybe do R3. That's UV is equal to U1 V1 minus 2U2 V2 plus U3 V3. Is this a inner product? Okay. So is this an inner product? Well, so this is the one I mentioned. So you always want to check the easy ones first. So one of the easier ones to check is I always do this one first. Where is it? You typically always do number 4 first, because that one's probably the easiest one to check to see if it's satisfied or not. But so let's check that one first. So note that let's say u is equal to, I don't know, the vector 1, 2, 1. Oh, it says right there, 220. We have inner product. So if you take this thing with itself, this will give me 1 times 1 minus 2 times 2 times 2 plus 1 times 1 times 1, which is -6. Okay, so is this allowed? What I got out here? No. What should it be? Should well, not 0, but it has to be positive, right? Yeah, it has to be non-negative. So it's allowed to be 0 or any positive number, but not negative. So not a inner product. Okay. It's you. It's just both of them are used. But my V's are like this. My U's are like that. I try to distinguish them like that so you don't get confused. But I guess it's not working. Okay. Let's do one more example and then talk about lengths and all that stuff. So, example. Yeah. It has to be for all vectors. Yeah. So I guess maybe I should do that one person. So yeah, so this has to be true for every vector. So for every u, v, and w, it has to be true. All this has to be true for every single vector in the vector space. So if you can find one vector in the vector space that breaks it, then it immediately is not an inner product. Okay. So taking an example and showing that it breaks it, it says that that's not an inner product. Okay. So let's go over here. So example 5.2, what was this last one? Okay. Show that is a inner product in the vector space C of continuous functions on the interval a to b with your standard operations on the functions over, say, R. So we have to now show that this thing is an inner product. So we'll go through them all fast, but it's the same idea basically. So one, we need to show that we need to show that FG is equal to GF, right? Okay, so take the inner product of F and G. What is this equal to? Well, this is integral from A to B of f of x and g of x dx, right? So again, what are these things now? So if you evaluate a number, on a function, what is that object now? But just think about it, right? Just take any function and evaluate a number on it. What do you get? A number, right? Yeah, so these are real numbers, so they commute, right? So this is just going to be integral from g of x, f of x, dx. So they commute. I mean, integral of x squared cosine of x is the same thing as integral of cosine times x squared, right? So this is now G, F. Perfect. Okay. Next, let's show the distribution thing. So 2, we need to show F G plus H is equal to F G plus F H. Okay. So take F G plus H, which is equal to integral from A to B of F of X times G of X plus H of X, right? Dx. All right, so distribute. You get F of X, G of X plus F of X, H of X dx. Well, you know that, yeah, I can go back. So you know that integration distributes over sums. So you can use that right there for the very next step. And since you have that, and that it basically becomes what you were looking for. Okay, are you good with the slide? Okay, perfect. So now this is going to equal to integral a to b f of x g of x dx plus integral from a to b f of x h of x dx, right? So this thing right there is just the inner products of f and g. This thing right here is just the inner product of f and h. And so we showed it. Perfect. 3. We just need to show that c times fg is equal to cfg, right? So do cfg. Well, this is equal to c times the integral a to b f of x dx. Oh, sorry, g of x dx. Well, constants, you can pull them inside integration, right? So this is just going to be integral from a to b of c f of x g of x dx, and then just associate this. And then you have what you're looking for. So this is equal, oops. So inner products, oops, there it is, G. Okay, and then the last one, we just need to show that the inner product with F with itself is always positive, and what was, oh yeah, and this is 0 if and only if F is the 0 function, right? Okay, so inner product with F with itself. What is this going to give me? Well, it's going to be a to b of f of x dx. Well, this is just going to be integral from a to b of f of x squared d of x, right? All right, so from here, is this integral always going to be positive? But just think about it, right? When is my integral positive? Well, if you think of it in terms of area, right? It happens only with when the graph is above the x-axis, right? Well, I mean, it can go under, but as long as the one that's under is less than the one on above, the area, and when they add them together, it's positive, right? But the question is, it will be more like this. It won't be a true and false quotient. It will be like this, yeah. So I'll just ask, is this an inner product? And then you'll have to like do the 4 steps. Yeah, okay, so when is my graph above the x-axis? Well, what is, I mean, just think of it as like in coordinates, right? In coordinates, it's if it's above the x-axis, so y has to be positive, right? So what is representing here is to be y, f of x, right? Remember, y equals f of x. So is my y coordinate always going to be positive? Yeah, f of x squared is always going to be positive, so yes. So this is definitely always going to be greater than or equal to 0. And the integral from a to b of, I guess, f of x dx squared equals 0. Okay, so there's two ways for this to be 0. One is if you integrate over a symmetric interval of a odd function, right? Because if it's an odd function, you would have this, right? So for example, this is an odd function. And if you do the symmetric interval, these two areas will combine and annihilate each other, right? It'll be 0. That's one way. What about the other way? I mean, is this ever going to happen for our f of x squared? No, right? So the only other way for it to happen is if the area underneath the curve is completely 0, which happens when it's 0, right? If f was 2, for example, the constant 2, there will still be area over it, right? Like this. So we know f of x is positive. It means it's always in the top. So if the line was up here, you still have area. The only way that you'll have no area is if it doesn't go below the x-axis, is if that line was down here, right? Which represents the line y equals 0 or f of x equals 0. So yeah, exactly. So which this implies that f of x has to equal 0. In real analysis, if you ever take it, you'll make this more precise. This is more like a hand wavy kind of proof, but regardless, this is fine for our purposes. But yeah, so this thing is an inner product on our space. Okay. I think now we're almost ready to define what it means to be a length, an angle, and I guess a distance, right? So let us now state one theorem, which is just some properties of inner products. So let U, V, and W be in, say, a vector space V over a field F, and C be a scalar in my field. Then the following are true. So one, the inner product between the 0 vector and any vector V is always just going to be V. Well, I mean, this literally just comes from the definition, so I shouldn't just. So it's true for, I guess maybe I should say it's true for both sides. So this is always just going to be 0, okay? And if the field, in the field you have a concept of 0, but for real numbers it's just 0. The normal notion of 0. The inner products between the W. Well, this is just an extension of the other one. And then 3. So now U, C, V is equal to C, U, V. Okay, so these are always true. Now we can define what it means. Now we're ready to define distance, length, angle, and orthogonal in the more general sense that we've than we already know. Okay. All right. All right. All right. So definition. Or I should say maybe just put def. Okay. So let U and V be vectors in a vector space V over a field F. Then we have these definitions. One, the length of, I guess, say V is what we call the norm of V, which is given by the square root of the inner product of V with itself. Okay. So another important thing is that once you have an inner product on a vector space, you can always induce a norm on it this way, always. Two, the distance between U and V is, well, d of uv, which is the distance between them. This is just going to be the norm of u minus v, right? And the norm is how it's defined right above that. The angle between two, I guess, non-zero vectors, u and v, is, well, it can be found using, I guess, cosine inverse, but it can be found I guess you can say maybe more can be found using cosine of theta, which is now going to be, okay, so originally it was the dot product, but now it's going to be u inner product with v divided by the norm of u, norm of v. And the norm again is how it's defined up there. So this is now how you, so if you find this and then take the cosine inverse on both sides, you get the angle. Okay. And then U is orthogonal to V if the inner product between U and V is 0. Okay, so now you know what it means to be a distance away from another vector, a length of a vector, an angle between two vectors, and what it means to be 90 degrees between each other, right? In the more general sense, like you know, not vectors like in Euclidean space anymore. All right, so let's see. Oh, that. So let's do maybe one example. We'll do one example, and then we'll go on to projections. Yeah, so we'll do one example on this stuff, and then well, bracket UV is always going to be a enterprise. So it's not going to be a vector. So it's a real number. It's a scalar, right? So I'm not understanding. So what do you mean, like? Do you mean like would it be? So hold on, let me think. I'm trying to think like where the confusion might be. So this is always going to be a number. In our cases, I guess, a real number. It's always going to be a real number. And I'm always going to denote this thing as an inner product. Okay, this is always going to be an inner product for us. I think you mean like this, right? Maybe like this. Wait, because I remember seeing this, like the I plus JK one. This one. Yeah, I think this one is the one you might be referring to. Yeah, so if it has two things as an inner product, yeah. Yeah, because I don't think I ever in calculus. I think really the only ones you use is this notation right here when you do the cross product, and then yeah. So no, this is standard. This is standard notation. I'm not just like making it up. Like this is like when you see inner products, they always denote it this way. I know in physics they have one like like this, but that's not an inner product. That's just I guess they're I think they say bra and ket vectors or whatever. But yeah, no, ours if it has like a comma, then it's a inner product. Okay, so let's see. Okay, 5 minutes. So let's do one example. So example, let's say, what's it? 5, 2, 3, 5, 2, 4. What is the, I guess you could say, length of f of x equals x squared in the vector space 0 to 1 with standard notation over the real numbers with the standard inner product. So what I mean by standard, I mean this one right here. So I'm always going to refer to the standard inner product for continuous functions to be this thing right here. Okay. All right. So what is the length again? How is it defined? So just look there, right? It's just the norm, right? So it's going to be, so the norm of f, which is going to equal to the square root of the inner product of f with itself, right? But what's the inner product? Well, it's just going to be the integral of f of x squared dx, and since here a and b are 0, it's just gonna be 0 to 1. So that's just gonna be the square root of the integral from 0 to 1 of, I don't know, say, so it was x squared, so it'd be x to the 4th. Dx. So I don't know, just do just do the integral, right? So it's just going to be the square root of x to the 5 1/5 0 to 1 1/5. So yeah, it's just going to be 1/5, right? Or 1 over square root of 5. So that's going to be the length of x squared in this vector space with this inner product. Okay. So I guess maybe you just write one more theorem down, and then I'll call it a day from there. Right, 1, 2, 1, 5, 2. So let U and V be in the vector space V plus dot. Then we have these things. So we have the Cauchy-Schwarz as well. Cauchy-Schwarz. So remember Cauchy-Schwarz in the Euclidean space? Well, we have the same thing here. So the absolute value of U, V of the inner product. It's always going to be less than or equal to the norms of U and the norm of V. Okay. 2, we have the triangle inequality here too. Which means that we have the norm of U plus V is less than or equal to the norm of U plus the norm of V. Oops. And then 3, we have Pythagoras Theorem equivalent here as well. So meaning we have U plus V, all this squared is equal to U squared plus V squared. Yeah. So now we're going to probably use this a bit more later, but so now we have the notion of distance, length, angles, and all that stuff for general vector spaces. So the next thing we're going to do is basically we're going to talk about projections. So you guys might have already done projections and maybe like projected things onto the x-axis. So remember in maybe physics when you add like how you get the resultant vector for a force, you like project it onto the x and the y and add them. Well, we'll do a similar thing here, but instead of projecting to the x and y axis, we'll project it onto any arbitrary vector and soon a subspace. Okay, you guys can now go. Yeah, for sure. I'll do it right now. What is next week? No, we still have time before next week, right? So The what? Oh yeah, I have to get to that. Yeah, I'll do it soon. Oh yeah. I mean, you could, I guess, calculate what you have just based on that syllabus, the number of points. Just convert those to percentages, and then you can like find out what you have. But I'll do that as well soon, so don't worry. Yeah. So, all right. So, sorry, but just send. Okay, perfect. All right. I'll see you guys later.